Out there in the vast black ocean of space, where darkness stretches beyond comprehension, galaxies spin like cosmic whirlpools, each one hiding secrets that defy explanation. Among them, a brilliant spiral known as the Pinwheel Galaxy gleams with a promise of mystery. Officially catalogued as M101, this celestial wonder isn't just another pinprick of light. It's a realm where the ordinary rules of the universe seem to bend, where stars behave in ways that leave astronomers speechless, and where whispers of phenomena we can't yet explain linger like echoes in the void. Picture a galaxy so massive it dwarfs our own Milky Way, its arms swirling with over 1 trillion stars, each one a potential sun to alien worlds we've yet to discover. But the real magic lies in the anomalies, the bizarre, the unexplained, the downright eerie. Imagine stellar nurseries birthing stars at impossible speeds, regions where gravity itself appears to malfunction, and strange, rhythmic signals that some speculate could be more than just natural cosmic noise. The Pinwheel Galaxy isn't just beautiful, it's a puzzle wrapped in stardust, and every new observation peels back another layer of its secrets. This journey will take you through 30 of its most baffling enigmas, from freakish celestial objects that shouldn't exist to unexplained structures that challenge everything we know about galaxy formation. Could some of these phenomena hint at intelligence beyond our own? Or are we witnessing the raw, untamed power of the universe in ways we've never seen before? Strap in, because by the time we're done, you'll see the Pinwheel Galaxy not just as a distant speck of light, but as a living, breathing frontier of cosmic mystery waiting to be explored. One of the first things astronomers noticed about the Pinwheel Galaxy was something deeply unsettling. It shouldn't look like this. Most spiral galaxies, including our own Milky Way, boast near-perfect symmetry, their arms curling outward in a balanced cosmic dance. But the pinwheel, its spiral structure is twisted, lopsided, almost as if some unseen hand reached in and warped it. One side stretches far longer than the other, while dense clusters of stars bunch up unevenly along its arms, defying the elegant order we expect from such a massive galaxy. So what's causing this cosmic imbalance? One leading theory points to gravitational encounters with neighboring galaxies. Over millions of years, close passes by other massive objects could have tugged at the pinwheel's delicate structure, distorting its shape like a game of celestial tug-of-war. Yet, when scientists mapped nearby galaxies, none seemed close enough or massive enough to explain the sheer scale of this asymmetry. That's where dark matter enters the mystery. Some researchers speculate vast, invisible clumps of dark matter might lurk near the pinwheel, their gravitational pull warping the galaxy from within. Imagine an unseen anchor hidden in the depths of space, dragging one side of the galaxy out of alignment, except no one can find the anchor. Hubble's razor-sharp images reveal the irregularity in stunning detail. Glowing knots of star formation bunch up along one arm, while the opposite side appears stretched thin, its stars scattered like breadcrumbs trailing off into the void. This isn't just a quirk of perspective, it's a fundamental oddity written into the galaxy's very structure. And if dark matter truly is the culprit, the pinwheel's lopsided arms might hold clues to one of the universe's greatest unsolved puzzles: the nature of the invisible glue holding galaxies together. The deeper mystery, this asymmetry isn't just a cosmetic flaw. It's reshaping how we understand galaxy evolution. If the pinwheel's imbalance stems from some unseeable force, what else might be hiding in the dark between the stars? While many galaxies flicker with the occasional stellar explosion, the Pinwheel Galaxy practically crackles with them like a cosmic fireworks display stuck on repeat. Astronomers have catalogued more supernovae here than in most galaxies of its size, making M101 a hotspot for dying stars that go out in spectacular fashion. One of the most famous SN 2011 Phi wasn't just another flash in the dark, it was a Rosetta Stone for astrophysics. a pristine, textbook example of a Type Ia supernova, so perfectly observed it rewrote how we measure the universe's expansion. But why does the pinwheel produce so many of these cataclysmic events? The answer lies in its frenetic star-forming regions where gas and dust collide in a chaotic dance. Most galaxies have pockets of stellar birth, but M101's spiral arms are practically overflowing with them, dense, glowing nurseries where massive stars are born, live fast, and die young. These aren't just any stars, they're titanic beasts some dozens of times heavier than our Sun, burning through their fuel in mere millions of years before collapsing in explosions so bright they outshine entire galaxies. What's truly bizarre is how these supernovae seem to cluster. Instead of scattering randomly, they often erupt in chains, like dominoes toppling across the galaxy's arms. One theory suggests shockwaves from earlier explosions compress nearby gas clouds, triggering new star formation, and eventually more supernova. It's a self-perpetuating cycle, death breeding life, and life destined for fiery death. The aftermath is just as fascinating. These explosions don't just vanish, they seed the galaxy with heavy elements: oxygen, iron, even gold, scattering the building blocks of planets and life across the cosmos. In a way, every supernova in the Pinwheel Galaxy is a sculptor, reshaping its structure and chemistry with each detonation. And with so many going off, M101 might just be one of the universe's great recycling centers, turning stellar ashes into the raw materials for new worlds. Yet for all we've learned, a question lingers. Could this supernova surplus hint at something even stranger? Some astronomers speculate that the pinwheel's extreme star formation might be fueled by hidden forces, perhaps dark matter interactions or past galactic collisions we've yet to uncover. Every explosion isn't just a flash of light, it's a clue waiting to be deciphered. Deep within the swirling arms of the Pinwheel Galaxy lies a cosmic paradox, a gaping void where there should be chaos. Hydrogen, the universe's most abundant element, usually fills galaxies like a thick, swirling fog, the raw fuel for star birth. Yet here, spanning an astonishing 15,000 light-years, stretches a near-perfect sphere of near-nothingness. It's as if some cosmic vacuum reached in and sucked away the galaxy's lifeblood, leaving behind a ghostly cavity in the interstellar medium. At first glance, the void's sheer scale defies explanation. To carve such a hole would require energy beyond imagination, equivalent to millions of supernovae detonating in unison. One leading theory points to the galaxy's supermassive black hole hidden at its core. While quieter than most, it might have erupted in the past, firing jets of plasma at near-light speed like cosmic blowtorches. These jets could have punched through the galaxy's gas clouds, sweeping hydrogen aside like a snowplow clearing a path. But there's a problem. The void shape doesn't perfectly align with the black hole's axis, leaving astronomers puzzled about the true source of this clean, spherical emptiness. Then there's the dark matter hypothesis. Some suggest an invisible dwarf galaxy, made mostly of dark matter, might have barreled through the pinwheel eons ago. Like a bullet through smoke, its gravitational wake could have scattered the hydrogen, leaving this eerie hollow behind. The idea tantalizes researchers because it would mean dark matter, already mysterious, can reshape visible matter in ways we're only beginning to understand. Yet no trace of such an intruder has been found, not even a telltale stream of stars torn loose by the encounter. What makes this void even stranger is its impact on star formation. Around its edges, hydrogen piles up in dense waves, triggering frenzied stellar births. It's as if the galaxy, wounded by this inexplicable absence, is trying to heal itself by overcompensating at the borders. Telescopes like ALMA have captured these ripple effects in stunning detail, bright knots of new stars flaring to life where gas collides at the void's rim, sketching a glowing ring around nothingness. The most unsettling possibility, this might not be a one-time anomaly. If such voids can form without obvious causes, how many other galaxies hide similar blank spots in their hydrogen maps, and what unseen forces might be responsible? The Pinwheel's hydrogen hole isn't just an absence, it's a silent scream, challenging us to rethink how galaxies live, breathe, and evolve. Nestled among the Pinwheel Galaxy's spiral arms, there's a class of objects so energetic they blur the line between science and science fiction. Astronomers call them ultraluminous X-ray sources, ULXs for short, and these cosmic powerhouses emit more X-rays than should theoretically be possible. Imagine a single object outshining a million suns, all in high-energy X-rays that pierce through dust and gas like celestial searchlights. What's baffling isn't just their brightness, but the fact that they exist at all. According to our current understanding of physics, nothing should be able to produce this much energy without collapsing into a black hole. Yet there they are, pulsing away, defying every rule in the astrophysics playbook. At first, scientists suspected these were intermediate mass black holes, cosmic middleweights bridging the gap between stellar black holes and the supermassive giants lurking in galactic cores. These elusive objects, theorized but never definitively observed, could explain the ULK's outrageous energy output. But when telescopes like Chandra and new stars zoomed in, the data told a stranger story. Some ULXs flicker rapidly, their X-ray output rising and falling in hours, a behavior too fast for anything but small, dense objects. Others seem to orbit companion stars, pulling material away in sizzling streams of plasma that glow with the heat of 100 million degrees. Then came the real curveball. A handful of these sources appear to be neutron stars, the crushed cores of dead stars so dense a teaspoon of their material would outweigh Mount Everest. Neutron stars have strict energy limits, like cosmic speed limits baked into the laws of physics. Yet these ULXs are blowing past those limits as if they don't exist. Some researchers suggest these neutron stars might be magnetars with insanely powerful magnetic fields, twisting space-time itself to funnel energy into focused X-ray beams. Others propose they're surrounded by thick, donut-shaped clouds of gas that act like lenses, amplifying their emission to deceptive levels. The implications ripple far beyond the Pinwheel Galaxy. If ULXs are rewriting the rules for how compact objects behave, they could force us to reconsider fundamental aspects of gravity, accretion physics, and even the life cycles of stars. Every flicker, every pulse from these enigmatic sources is a coded message, one we're only beginning to decipher. And with each new observation, the Pinwheel's ULXs whisper a tantalizing question. What if we've only scratched the surface of what's physically possible in the universe? Tucked away in the outer fringes of the Pinwheel Galaxy, where the grand spiral arms begin to fade into the black, there's a cosmic structure so peculiar it looks like it was drawn with a ruler. Astronomers call it the Red Rectangle, not the most imaginative name, but one glance explains why. While most nebulae billow in organic, cloud-like swirls, this one forms near-perfect geometric shapes, concentric rectangles stacked like a glowing honeycomb, their sharp corners defying the chaos of space. It's as if someone took the concept of a nebula and forced it into an architectural blueprint, creating a celestial structure that simply shouldn't exist under normal cosmic rules. At the heart of this geometric wonder lies a dying star, one that's been shedding its outer layers in a slow, precise ballet. Most aging stars expel material in messy, asymmetrical bursts. Think of a balloon deflating in random spurts. But here, the star seems to be ejecting gas and dust in carefully controlled jets, sculpted by some unseen force into this uncanny symmetry. The leading theory involves a dense disk of material surrounding the star, funneling its dying breaths into opposing cones. As these cones expand, we see them edge on from Earth, their intersecting edges creating the illusion of stacked rectangles. It's nature's version of a laser light show with stardust as the medium. What makes the red rectangle truly bizarre isn't just its shape, it's the color. most planetary nebulae shimmer in blues and greens, energized by the ultraviolet radiation of their central stars. But this one burns a deep, rusty red, thanks to exotic carbon-rich molecules called polycyclic aromatic hydrocarbons. These complex organic compounds, often found in candle soot or car exhaust on Earth, are floating in space here, fluorescing under starlight like cosmic neon signs. Some scientists even speculate these molecules could be the precursors to life's building blocks, hinting that death in this corner of the Pinwheel Galaxy might be sowing the seeds for new beginnings. Yet mysteries linger. Why is the red rectangle so perfectly aligned? For the geometry to appear this crisp from our vantage point, the star's disk and jets would need to be tilted at an exact angle toward Earth, a statistical improbability unless such structures are far more common than we've observed. Even stranger, similar rectangular nebulae have been spotted in other galaxies, suggesting this isn't just a fluke. Could there be an undiscovered law of stellar death that favors symmetry? Or is the universe quietly hiding more of these geometric ghosts, waiting for us to adjust our telescopes and see them for what they truly are? The red rectangle doesn't just challenge our understanding of how stars die. It blurs the line between chaos and order. In a cosmos where randomness reigns, this nebula stands as a quiet rebel, a reminder that even in the vast, untamed wilds of space, precision can emerge from the most unlikely places. And as it slowly fades over millennia, its perfect angles dissolving back into the void, it leaves behind a question etched in stardust. How many other cosmic rule breakers are out there hiding in plain sight? At the very heart of the Pinwheel Galaxy, where supermassive black holes and violent energies typically dominate, telescopes have picked up something far stranger, a persistent infrared glow with no clear source. This isn't the usual warmth of starlight or even the scorching heat of accretion disks. It's a diffuse, enigmatic radiance that blankets the galactic center like a ghostly shroud, emitting wavelengths that suggest temperatures far too uniform to stem from any known cosmic process. Most galaxies show infrared signatures near their cores, but this one defies expectations, glowing brighter and more mysteriously than astrophysicists can easily explain. The leading theory points to vast clouds of heated dust, fine particles warmed by hidden stars or the black hole's furious energy. Yet when researchers mapped the glow's distribution, it didn't match the expected patterns. Instead of concentrated rings or spirals, the infrared light spreads in odd, asymmetrical patches as if something, or someone, had scattered embers across the galaxy's core. Some regions shine far brighter than others, with no obvious stellar sources to account for the intensity. It's like walking into a room illuminated by unseen light bulbs, their positions and power sources completely concealed. Then there's the timing. Infrared surveys over the past 2 decades reveal the glow isn't static. Some sections flicker subtly, brightening and dimming over months or years, behavior dust alone shouldn't exhibit unless stirred by unseen forces. Could colossal, hidden star-forming regions lie buried beneath opaque veils of gas, their newborn stars heating the dust from within? Or might exotic physics be at play, like the slow decay of hypothetical particles left over from the galaxy's formation? The most tantalizing possibility involves the black hole itself. While the Pinwheel's central black hole appears unusually quiet, some astronomers speculate it might be feeding in ways we've never observed, its gravitational energy converted into infrared radiation through mechanisms we don't yet understand. Others suggest the glow could be the collective warmth of thousands of densely packed stars, crammed into a space so tight even our best telescopes can't resolve them individually. What's undeniable is how this infrared enigma challenges our assumptions. If something as fundamental as a galaxy's heat signature can elude explanation, what else might we be missing in the shadows between the stars? Every wavelength of light tells a story, and the Pinwheel's mysterious glow is a paragraph we're still struggling to read. Buried within the Pinwheel Galaxy's grand spiral arms, radio telescopes have uncovered something haunting, a ghostly echo of structure lurking just beyond the visible light. This faint secondary spiral, detectable only in the whisper-quiet wavelengths of radio emissions, coils through the galaxy like a cosmic afterimage. It's not just a wisp of gas or a trick of perspective. This phantom spiral mirrors the galaxy's dominant shape, but with a twist. Its arms are offset, trailing slightly behind the bright, star-filled ones we see in optical images. The disconnect is so precise it feels intentional, as if the galaxy is moving to a rhythm only part of it can hear. So what could create such an eerie silhouette? One camp of astronomers argues for a violent past the aftermath of a galactic merger. Imagine another, smaller galaxy plowing through the pinwheel billions of years ago, its stars and gas ripped apart by tidal forces. As the debris settled, it could have formed this faint counterpoint to the main spiral, a fossil record of celestial carnage frozen in time. Supporting this, the radio waves reveal tendrils of hydrogen gas stretching far beyond the visible disk like scars from a long-healed wound. Yet there's a problem. The pinwheel's core shows no signs of the chaos such a collision would leave behind. Most merged galaxies bear telltale distortions, twisted star clusters, erratic black hole activity, but here the center remains eerily calm. That's where the alternative theory gains traction. Instead of a cataclysm, the phantom spiral might be evidence of something subtler, resonances. Like vibrations in a drumhead, density waves can ripple through a galaxy's disk, compressing gas and triggering star formation in predictable patterns. The primary spiral arms could be sculpted by one set of waves, while the phantom spiral responds to another, slower rhythm, a harmonic echo in the galaxy's rotation. Radio observations show the gas in this secondary structure moving at slightly different speeds, as if dancing to its own tune. If true, the pinwheel isn't just a static beauty. It's a dynamic system humming with hidden frequencies, its structure far more complex than a single snapshot suggests. The most puzzling detail, the phantom spiral stars. While its gas glows brightly in radio, optical telescopes struggle to spot accompanying starlight. This disconnect suggests the structure might be a nursery in stasis, a place where gas hasn't yet collapsed into stars or where conditions prevent star birth entirely. Some researchers speculate magnetic fields could be stifling the process, their invisible lines of force propping up the gas like scaffolding, keeping it suspended in a kind of cosmic limbo. Others wonder if dark matter's gravitational influence is warping the region, subtly altering the rules of stellar formation. What makes this phenomenon so compelling is its duality. It's both a relic and a living puzzle, a structure that could either be the ghost of a long-dead galaxy or a fingerprint of the pinwheel's hidden mechanics. As radio arrays grow more sensitive, the phantom spiral's secrets may finally come into focus. Until then, it lingers like a question written in hydrogen, challenging us to reconsider how galaxies evolve, interact, and sing their silent songs across the eons. Among the Pinwheel Galaxy's countless stars, a handful behave like cosmic fugitives blazing across space at speeds so extreme they're destined to escape the galaxy entirely. These hypervelocity runaway stars don't just drift, they hurtle outward at over 1 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes. Their trajectories slash through the galaxy's spiral arms like knife cuts, pointing backward to violent origins astronomers are still piecing together. Take one infamous example, a blue supergiant designated HVS 1017. Unlike most stars, which orbit placidly around the galactic center, this one races toward intergalactic space at nearly 3 million miles per hour. Its path, traced backward, leads straight to a dense star cluster near the pinwheel's core. The likely culprit, a supernova kick. When a massive star explodes in a binary system, the sudden loss of mass can send its surviving companion rocketing away like a slingshot released at full tension. In HVS 1017's case, the force was so brutal it didn't just escape its birthplace, it breached the galaxy's gravitational grip entirely, doomed to wander the void between galaxies forever. But supernovae aren't the only engines capable of such stellar catapults. Near the Pinwheel's central black hole, stars skirt the edge of oblivion where gravity becomes a weapon. A few may have been part of binary systems that ventured too close. As one star was captured and devoured, its partner could have been flung outward at unimaginable speeds. This slingshot effect, predicted by Einstein's equations, transforms black holes into cosmic particle accelerators, ones that launch stars like bullets from a rifle. What's truly startling is where these runaways end up. While most will fade into the darkness between galaxies, a rare few might collide with other star systems millions of years from now. Imagine the spectacle: a star born in the Pinwheel Galaxy suddenly intruding upon another galaxy's outskirts, its light telling a story of interstellar exile written in fire and momentum. Yet the biggest mystery isn't their speed, it's their composition. Spectroscopic analyses reveal some hypervelocity stars carry unusual chemical signatures like oxygen or neon-rich atmospheres. These elements, typically forged in supernova furnaces, suggest these stars weren't just bystanders to violence. They may have been scraped by the explosions themselves, their surfaces coated in stellar shrapnel from their dramatic escapes. The Pinwheel's runaway stars aren't just curiosities, they're celestial speedometers. By tracking their paths, astronomers can map the hidden gravitational landscape of the galaxy, inferring the mass of its black hole and the distribution of dark matter that tugs at their trajectories. Each one is a probe flung into the cosmic dark, tracing the invisible architecture of space itself. And as more are discovered, they whisper a tantalizing truth. Sometimes, to understand where a galaxy is going, you must first chase the stars it's left behind. Hidden within the Pinwheel Galaxy's spiral arms lies a cosmic contradiction. A cluster of stars weighing as much as a small galaxy, yet glowing so faintly it barely registers on telescopes. Officially catalogued as M101 Dark Star Cluster 01, this enigma packs the mass of over 200,000 suns into a tight sphere, but emits less light than a single supergiant star. At first glance, it defies logic. How can something so massive remain so dim, like a mountain hiding in a shadow? Theories abound, but none neatly solve the puzzle. One possibility points to a graveyard of failed supernova stars so massive they should have exploded, but instead collapsed directly into black holes without the usual fireworks. Picture a stellar generation where every member met this quiet fate, leaving behind a swarm of invisible remnants. These black holes would still exert gravitational pull, explaining the cluster's heft while contributing almost no light. Supporting this, infrared surveys detect faint heat signatures consistent with accretion, disks whispers of material spiraling into unseen voids. Yet even this doesn't fully account for the cluster's eerie uniformity. If black holes dominate, why haven't they merged or devoured nearby stars, creating detectable flares? Then there's the dark matter angle. Some astrophysicists suggest the cluster might be drowning in a localized halo of this mysterious substance, its gravitational grip preventing normal stars from forming or surviving. Imagine a cosmic dead zone, where dark matter's dominance stifles stellar birth and starves existing stars of the gas needed to shine brightly. Radio observations reveal unusual hydrogen depletion in the area, as if something has siphoned off the raw material for star formation. But dark matter halos typically envelop entire galaxies, not isolated clusters, making this a potential first. The most tantalizing clue comes from the cluster's surviving stars. Those few that do glow exhibit bizarre chemical signatures, rich in elements like carbon and nitrogen but lacking heavier metals. This peculiar mix suggests they formed in an environment starved of supernova debris, the very material that usually seeds new generations of stars. It's as if the cluster's history froze midway, cutting off the cycle of stellar life and death. What makes this dark cluster truly unsettling is what it implies about galactic evolution. If such objects are more common than we've realized, they could rewrite our understanding of how star clusters age, and how much of a galaxy's mass might lurk unseen, not as diffused dark matter, but as concentrated shadows. The Pinwheel's dark star cluster isn't just an oddity, it's a cosmic mirror reflecting how much we still don't see in the night sky. High above the Pinwheel Galaxy's luminous disk, stretching tens of thousands of light years into the void, two colossal gamma-ray bubbles loom like silent titans. Discovered by the Fermi Space Telescope, these immense structures glow with the highest energy light in the universe, forming a faint hourglass shape that dwarfs the galaxy itself. At first glance, they resemble the Fermi bubbles above our own Milky Way, but these are far more intense, pumping out gamma rays with a ferocity that defies easy explanation. The leading theory points to the galaxy's central supermassive black hole. Though quiet now, it may have erupted in a cataclysmic outburst millions of years ago, spewing jets of relativistic particles at near light speed. These jets slamming into intergalactic gas could have inflated the bubbles like cosmic balloons, their shockwaves accelerating particles to energies that emit gamma rays upon collision. Imagine a black hole's tantrum so violent it left scars visible across interstellar distances, an echo of fury frozen in high-energy light. But there's a twist. Detailed spectral analysis reveals gamma-ray patterns that don't perfectly match known black hole jet models. Some wavelengths suggest an alternative origin, dark matter annihilation. If certain theoretical particles like weakly interacting massive particles or WIMP collide and annihilate in the galaxy's halo, they could produce gamma rays as a byproduct. The bubble's symmetry and scale align eerily with predictions of dark matter distributions, fueling speculation that we might be witnessing the universe's most elusive substance finally making its mark on the visible world. Compounding the mystery, the bubbles aren't static. Fermi's decade-long observations show subtle fluctuations in their gamma-ray output, as if some unseen process within them remains active. If linked to dark matter, this flickering could hint at dynamic interactions in the galaxy's invisible halo. If tied to the black hole, it might suggest a cycle of dormant and active states far more complex than we've assumed. What makes these structures so captivating isn't just their origin, it's their reach. The bubbles extend far beyond the Pinwheel's starry disk, a reminder that galaxies aren't flat islands but dynamic systems embedded in vast, interconnected webs of energy and matter. Their gamma-ray glow illuminates the invisible architecture of space itself, tracing forces we're only beginning to comprehend. And as Fermi keeps watching, each new pulse of data brings us closer to answering a question that straddles the line between astrophysics and particle physics. Are we seeing the aftermath of a black hole's rage, or the first indirect glimpse of dark matter's hidden hand? Either way, the Pinwheel's gamma-ray bubbles aren't just a curiosity, they're a cosmic crossroads where the known and unknown collide with dazzling, high-energy consequences. The Pinwheel Galaxy's magnetic field isn't just invisible, it's broken. Normally, spiral galaxies like ours have orderly magnetic fields that follow their spiral arms, tracing the graceful curves of star formation like cosmic fingerprints. But M101's magnetic lines are tangled, twisted into chaotic knots that defy conventional models. Some regions show field lines abruptly snapping backward, as if space itself has developed a short circuit. Others reveal bizarre loops and walls like a spiderweb caught in a hurricane. This isn't just random noise, it's a systematic distortion that suggests something fundamental is missing from our understanding of galactic magnetism. What could warp a galaxy's magnetic field so violently? One clue lies in the turbulent gas clouds between stars. Magnetic fields are woven into the fabric of interstellar space, threading through clouds of hydrogen like invisible wires. When those clouds collide or swirl, the fields can stretch, snap, and reconnect, a process called magnetic reconnection that unleashes staggering energy. In the Pinwheel, astronomers have detected supersonic gas flows rippling through its arms, potentially twisting the fields into these strange configurations. Imagine dragging a comb through wet hair. The strands snag, tangle, and eventually knot. Now scale that up to galactic proportions, where the hair is made of magnetic force and the comb is a shockwave from a supernova or a collision with intergalactic gas. But turbulence alone might not explain the field's most extreme distortions. Some sections appear to spiral inward toward the galaxy's core at sharp angles, as if tugged by an unseen force. This has led to wilder theories like the presence of primordial magnetic monopoles. These hypothetical particles, predicted by some grand unified theories of physics, would carry a solitary magnetic charge, either north or south, rather than the paired poles we're familiar with. If they exist, they could twist magnetic fields into configurations impossible under normal physics. While there's no direct evidence, the Pinwheel's aberrant field patterns offer a tantalizing hunting ground for such exotica. The most unsettling implication: this magnetic chaos could be reshaping the galaxy itself. Magnetic fields guide star formation, channeling gas into dense pockets where gravity takes over. If the fields are twisted, so too is the galaxy's ability to birth new stars. Infrared observations reveal star-forming regions in M101 that align suspiciously with its magnetic kinks, as if the field's distortions are herding cosmic nurseries into unnatural shapes. It's a feedback loop of cosmic proportions. Turbulence warps the field, the warped field redirects star birth, and newborn stars pump energy back into the system through winds and explosions, stirring further turbulence. The Pinwheel's magnetic field isn't just a curiosity, it's a laboratory. Every kink and tangle encodes information about forces we can't yet measure directly, from the microphysics of interstellar plasma to the potential influence of dark matter. And as astronomers map its twists with ever greater precision, they're not just studying a single galaxy's quirks. They're probing the invisible architecture of the universe itself, one magnetic snarl at a time. Deep within the Pinwheel Galaxy, a signal pulses with the precision of a cosmic metronome. Fast radio bursts, or FRB, erupting in repeating patterns that defy simple explanation. These millisecond-long flashes of radio waves pack more energy than the sun emits in weeks, and in M101 they've been traced to a region teeming with stellar wreckage. At first glance, the culprit seems obvious: neutron stars, the ultra-dense corpses of dead suns. Some of these spinning remnants, called magnetars, possess magnetic fields so intense they can crack their own surfaces, releasing bursts of energy like cosmic lightning. Yet the FRBs from the Pinwheel don't behave like typical magnetar flares. They repeat on schedules too erratic for simple stellar mechanics, flickering to life in sequences that suggest something far stranger at work. The leading theory involves a neutron star orbiting an unseen companion, perhaps a black hole or another dense stellar remnant. As the star plows through debris or interacts with its partner's gravity, it could unleash periodic shockwaves, accelerating particles to near light speed and generating those telltale radio spikes. Recent observations from the CHIME telescope reveal subtle frequency drifts in the bursts, like a radio dial being slowly twisted, hinting at a dynamic environment where plasma density shifts unpredictably. But here's the catch: some bursts arrive in clusters so tightly spaced that even this model struggles to account for them. It's as if the source flickers on and off like a malfunctioning switch, governed by rules we haven't yet deciphered. Then there's the speculative frontier, the possibility that these aren't natural phenomena at all. FRBs are eerily efficient at piercing through cosmic dust, their frequencies ideal for interstellar communication. Could they be engineered signals deliberately beamed across galaxies? The notion isn't as far-fetched as it sounds. In 1967, astronomers initially mistook pulsars for extraterrestrial broadcasts before uncovering their natural origins. The pinwheels repeating FRBs with their irregular cadences and localized origin revive that tantalizing question: are we witnessing cosmic physics or something more deliberate? What makes this mystery even thornier is the burst's polarization, the way their radio waves twist as they travel through space. Some display extreme Faraday rotation, a telltale sign of passing through intense magnetic fields. This aligns with neutron star theories, yet a handful of bursts show curiously clean polarization, as if their path was unexpectedly unobstructed. It's like hearing the same song played through two different speakers, one muffled, one crystal clear, from the same source. The pinwheel's FRBs aren't just scientific curiosities, they're probes. Each burst encodes information about the material it traversed, offering snapshots of the galaxy's hidden structure. And with every new detection, astronomers edge closer to an answer, whether it's a previously unknown state of matter around neutron stars, an exotic black hole interaction, or something beyond our current imagination. Until then, these enigmatic signals persist, stitching their cryptic patterns into the fabric of the cosmos. The Pinwheel Galaxy shouldn't be this lonely. According to our best cosmological models, massive spiral galaxies like M101 ought to be surrounded by swarms of dwarf satellite galaxies, small, faint companions held in orbit by their host's immense gravity. The Milky Way, for instance, has at least 60 known satellites, from the Large Magellanic Cloud to ultra-faint dwarfs barely visible against the cosmic backdrop. Yet the pinwheel, despite being larger and more massive than our own galaxy, appears almost deserted with fewer than a dozen confirmed satellites. This glaring discrepancy isn't just a quirk, it's a direct challenge to our understanding of how galaxies form and how dark matter sculpts the universe. The so-called missing satellites problem has haunted cosmologists for decades. Supercomputer simulations of cosmic structure, based on the prevailing lambda cold dark matter model, predict hundreds of tiny dark matter halos around galaxies like the pinwheel. These halos should act as gravitational seeds, pulling in gas to form dwarf galaxies. But when astronomers point telescopes at M101, most of those expected dwarfs simply aren't there. It's like expecting a bustling city skyline and finding only a handful of scattered streetlights instead. So where did they go? One possibility is that the dwarfs existed but were torn apart long ago. The pinwheel's gravitational tides could have shredded fragile satellites, scattering their stars into faint, nearly invisible streams. Hubble's deep imaging has revealed a few such ghostly tendrils around the galaxy, hints of past demolitions. Yet even accounting for this destruction, the numbers still fall short. Another theory suggests that many potential dwarfs never formed stars at all. Dark matter halos without enough gas to ignite stellar birth would remain invisible to optical telescopes, detectable only through gravitational lensing or gamma-ray signatures from potential dark matter interactions. But the plot thickens when we compare the pinwheel to its neighbors. The galaxy resides in a relatively sparse region of space, devoid of the massive galaxy clusters that might otherwise strip away satellites. This isolation makes the missing dwarfs even more perplexing. If the environment isn't to blame, the answer might lie in the nature of dark matter itself. Alternative theories like warm dark matter or self-interacting dark matter propose particles that move faster or collide more readily, suppressing the formation of small-scale structures. In these scenarios, the pinwheel satellite desert could be a cosmic fingerprint of dark matter's hidden properties. The most tantalizing clue comes from the few dwarfs that do orbit M101. These survivors, like the faint galaxy D101, show bizarrely high ratios of dark matter to visible stars, as if they're the last holdouts of a population that somehow failed to shine. Their existence suggests that the missing satellites might not be missing at all, but hiding in plain sight, cloaked in darkness. New radio telescopes like the Square Kilometre Array could soon scan the pinwheel's outskirts for the faint glow of hydrogen in these elusive halos, potentially rewriting the rules of galactic companionship. What makes this cosmic census so pivotal isn't just the gap between theory and observation. It's what that gap reveals about the universe's hidden scaffolding. The pinwheel's lonely reign forces us to confront uncomfortable questions. Are we overcounting dark matter's influence, underestimating the violence of galactic evolution? Or staring at the first hints of physics beyond our current models? Every absent dwarf is a silent challenge, a reminder that even in a universe brimming with light, some of the most important truths linger in the shadows. Scattered across the Pinwheel Galaxy's outskirts, far from the bustling stellar nurseries of its spiral arms, lie celestial rebels, young, blue stars burning defiantly in the cosmic wilderness. These outliers shouldn't exist. Hot, massive stars like these are the rock stars of the universe. They live fast, die young, and are almost always born in crowded, gas-rich neighborhoods. Yet here they are, shining in isolation like campfires in a desert, their intense ultraviolet light painting the surrounding void an eerie azure. Their very presence throws a wrench into our understanding of star formation, forcing astronomers to ask, how did these stellar misfits end up so far from home? One clue lies in their motion. Spectroscopic studies reveal many of these blue exiles hurtling through space at unusual speeds, their trajectories tracing back to the galaxy's vibrant spiral arms. This suggests a violent ejection, perhaps from close encounters with other massive stars, or even the gravitational slingshot of a black hole. Imagine a stellar game of pinball where a young star gets too close to a heavier sibling and is flung into the galactic hinterlands. But there's a catch. Some outliers show no signs of high velocity. They seem to have formed right where they are, in regions so devoid of gas that star birth should be impossible. That's where the rogue cloud theory comes in. Dense pockets of hydrogen gas torn loose from the galaxy's disk during collisions or tidal interactions could drift into these barren zones. Over millions of years, gravity might quietly compress these orphan clouds until, against all odds, they collapse into brilliant new stars. Hubble has spotted faint, filamentary wisps of gas near a few blue outliers, like cosmic umbilical cords trailing back toward the galactic disk. These could be the remnants of the very clouds that birthed them, their material now evaporated by the star's fierce radiation. The most perplexing cases, however, show no gas remnants at all. For these stars, astronomers propose an even wilder scenario: triggered formation by dark matter. If invisible dark matter clumps are denser in certain regions, their gravitational pull might subtly concentrate stray hydrogen atoms, creating just enough density to spark star birth in the void. It's a tantalizing idea, one that would link these stellar loners to the universe's most elusive substance. What makes these blue outliers more than just curiosities is their impact on the galactic ecosystem. Their powerful winds and eventual supernova enrich these desolate regions with heavy elements, seeding future generations of stars where none should exist. They're cosmic pioneers, blazing trails into the unknown and forcing us to rewrite the rules of where and how stars can be born. Every one of these azure renegades is a reminder that the universe still holds surprises even in its emptiest corners. At the heart of the Pinwheel Galaxy, where most supermassive black holes radiate with predictable ferocity, one celestial beast refuses to play by the rules. This black hole doesn't just consume matter, it flickers like a faulty cosmic light bulb, its brightness swinging wildly by factors of 10 over mere weeks. One month, it might shine with the intensity of 100 million suns. The next, it dims to near invisibility, as if a cosmic hand has turned a dial no one can see. These aren't the gradual fluctuations expected from feeding black holes. They're violent, unpredictable spikes and crashes that leave astronomers scrambling for explanations. The leading suspect lies in the black hole's accretion disk. the swirling maelstrom of superheated gas destined to vanish beyond the event horizon. Normally, these disks behave like orderly whirlpools with matter spiraling inward in a steady flow. But Hubble and Chandra observations reveal this one is different. It appears fragmented, riddled with clumps and gaps that collapse and reform like storm clouds in a hurricane. When dense pockets of gas suddenly plunge toward the black hole, they ignite intense flares of X-rays and gamma rays, the cosmic equivalent of logs tossed onto a fire. But the real mystery is what causes these instabilities. Some theorists point to magnetic turbulence, where tangled field lines snap and reconnect, flinging material inward in chaotic bursts. Others suggest the disk might be warped by the black hole's spin, its inner edge wobbling like a tilted plate and spilling matter erratically. Yet there's a stranger possibility: this black hole might not be dining alone. Infrared surveys hint at a second, smaller black hole circling the primary, its gravity stirring the accretion disk like a spoon in soup. Every close pass could trigger avalanches of gas into the central void, explaining the abrupt flare-ups. Such binary black hole systems are thought to be rare, but the Pinwheel's violent history of galactic collisions makes it a prime breeding ground for these gravitational tangos. If confirmed, it would mark the first time we've witnessed a paired black hole system directly influencing a galaxy's core activity in real time. The most puzzling aspect isn't the flares themselves, it's their color. As the black hole brightens, its light doesn't just intensify, it shifts toward higher energies, as if someone is cranking up the cosmic thermostat. This suggests the inner edge of the accretion disk is moving closer to the event horizon during outbursts, a phenomenon akin to a whirlpool suddenly narrowing its vortex. General relativity predicts such behavior, but never before have we seen it occur so rapidly and repeatedly. Each flicker becomes a laboratory for testing Einstein's theories under extreme conditions. What makes this flickering titan truly significant is its defiance of classification. Most active galaxies fall neatly into categories: quasars, Seyferts, blazars, each with distinct radiation patterns. This one straddles them all, morphing between types like a cosmic shapeshifter. Its capricious nature challenges our very definitions of how black holes interact with their surroundings, suggesting that the line between active and quiet galactic centers might be far blurrier than we thought. As telescopes train their lenses on this enigma, every flicker carries encrypted messages about the most extreme environments in the universe. Whether through magnetic chaos, hidden companions, or entirely new physics, the Pinwheel's restless black hole is rewriting the rules of cosmic gluttony, one unpredictable pulse at a time. The Pinwheel Galaxy's molecular clouds should hum with predictable chemistry, vast reservoirs of hydrogen and helium, peppered with trace amounts of heavier elements forged in stellar furnaces. But radio telescopes have uncovered a glaring oddity: sprawling regions where carbon monoxide, a common tracer of cold cosmic gas, appears in bizarre concentrations. Some zones brim with CO molecules at levels 10 times higher than models predict, while adjacent areas seemingly identical in temperature and density show near total absence. This patchwork quilt of molecular abundance defies every expectation of how gas should behave in a spiral galaxy, hinting at processes we've barely begun to unravel. At the heart of the mystery lies CO's unusual distribution. Normally, this molecule forms in the shielded hearts of dense gas clouds, where ultraviolet starlight can't break it apart. Yet in the Pinwheel, ultra-high-resolution images reveal CO thriving in exposed filaments along the galaxy's spiral arms, places where radiation should obliterate it. Even stranger, these CO-rich tendrils often coincide with zones of intense star formation, suggesting the gas isn't just surviving the stellar onslaught but might be actively catalyzed by it. One leading theory involves shock fronts from newborn stars compressing nearby gas, creating temporary pockets where CO forms at accelerated rates. Picture a cosmic domino effect. supernova waves squeeze gas, triggering molecule formation, which in turn cools the gas further, allowing more stars to ignite, a self-perpetuating cycle of creation and destruction. But the anomalies run deeper. In the galaxy's outer reaches, far from the radiation of young stars, CO appears in isolated clumps with no visible sources of heat or turbulence to explain its presence. These rogue clouds, rich in carbon monoxide but poor in other expected molecules like hydrogen cyanide, suggest an external origin, perhaps gas stolen from a smaller galaxy during an ancient collision. The Pinwheel's tidal streams, those faint rivers of stars stretching into the void, could be the smoking gun, trails left by a devoured companion whose molecular chemistry differed fundamentally from the host galaxies. If true, these CO pockets are celestial fossils, preserving the chemical fingerprint of a long-dead galaxy. The most tantalizing clue comes from isotopic ratios. CO molecules containing carbon-13, a rare heavy isotope, appear overabundant in certain regions. This imbalance points to enrichment by specific types of supernova, ones that produce carbon in unique proportions. Yet the pattern doesn't match nearby supernova remnants, implying these molecules might have been forged elsewhere and transported across the galaxy by stellar winds or dark matter-driven currents. What makes this chemical puzzle so pivotal is its link to life's ingredients. Carbon monoxide is a stepping stone to complex organic molecules, the precursors to amino acids and sugars. If the Pinwheel CO anomalies stem from exotic astrophysical processes, collisions, shock waves, or even dark matter interactions, they could reveal new pathways for chemistry in the cosmos. Every unusual concentration is a breadcrumb, leading us toward answers about how galaxies assemble their molecular building blocks, and whether those blocks might one day assemble something even more extraordinary. For nearly a decade, astronomers monitoring the Pinwheel Galaxy's gamma-ray emissions kept encountering the same maddening glitch, a brilliant flare appearing where nothing should exist, burning for weeks or months, then vanishing without a trace. Catalogued as GRS1709, this phantom source doesn't recur at regular intervals or linger like typical gamma-ray objects. It flickers to life at random, outshining the galaxy's active core before dissolving back into the background noise, leaving behind only frustration and questions. When first detected by the Fermi Gamma-Ray Space Telescope, researchers assumed it was a fluke, perhaps a distant quasar flaring up along the same line of sight. But repeated observations confirmed the source was intrinsically linked to the Pinwheel, localized to a sparse region between two spiral arms where no known gamma-ray emitters reside. Its spectrum defies classification, too sharp and narrow for a supernova remnant, too erratic for a pulsar, and far too fleeting for the jets of an intermediate black hole. It's as if someone is turning a cosmic blowtorch on and off in the void with no visible machinery behind it. The leading explanation points to pulsar glitches, sudden speed-ups in the rotation of highly magnetized neutron stars. When a pulsar's crust fractures under immense internal stresses, it can release stored rotational energy, causing the star to spin faster and emit gamma-ray bursts. But GRS1709's output dwarfs typical glitches by orders of magnitude, suggesting something more extreme. Some theorists propose a rare hyperglitch, where a pulsar's magnetic field undergoes a catastrophic reconfiguration, funneling vast energy into focused gamma-ray beams for weeks before stabilizing. Supporting this, archival X-ray data shows a faint neutron star candidate near the source's last known position, though why it would glitch so violently remains unclear. Then there's the particle acceleration hypothesis. Galactic magnetic fields can theoretically trap high-energy particles, creating temporary storage rings, where electrons and protons spiral near light speed, emitting gamma rays until the system destabilizes. The Pinwheel's twisted magnetic geometry might facilitate such ephemeral accelerators, especially in regions where colliding gas clouds generate shock waves. Yet no known process explains how these structures could form and dissipate so abruptly. The most tantalizing and controversial idea involves dark matter annihilation. If two weakly interacting massive particles WIMP collide in a dense dark matter clump, they could theoretically produce gamma rays as they annihilate. The irregular flickering might then reflect the clump's chaotic dynamics. While no definitive proof links GRS 1709 to dark matter, its capricious behavior aligns eerily with simulations of such interactions. What makes this gamma ray ghost so compelling isn't just its elusiveness, it's the way it forces us to confront the gaps in our cosmic inventory. Every reappearance offers fresh data, every disappearance deepens the riddle. Future observatories like the Cherenkov Telescope Array may finally catch this phantom in the act, revealing whether it's a known object behaving extraordinarily or something entirely new lurking in the shadows between the stars. Until then, it remains a fleeting signature in the gamma-ray static. A cosmic will owe the wisp daring us to chase it. Most galaxies spin like tops, their stars and gas swirling in a single flat disk. But the Pinwheel Galaxy might be hiding a secret, a cosmic hula hoop of stars and gas looping over its poles at a right angle to its main disk. This rare configuration, called a polar ring, has only been confirmed in a handful of spirals across the universe. If real, it would transform M101 from a textbook spiral into something far stranger, a galactic hybrid where two distinct structures share the same gravitational heart. The first whispers of this ring came from radio telescopes mapping hydrogen gas. While most of the pinwheel's gas follows its iconic spiral arms, faint filaments traced arcs perpendicular to the disk, streamers stretching tens of thousands of light-years above and below the galaxy. These ghostly trails didn't match the galaxy's rotation, suggesting they belonged to a separate system. Then came infrared surveys, revealing a faint smattering of stars along similar paths, some even bearing distinct chemical signatures from the main disk stellar population. Together, they paint the picture of a structure that doesn't belong, a celestial intruder frozen in an unlikely orbit. How could such a ring form? The leading theory involves a galactic theft of cosmic proportions. Billions of years ago, a smaller gas-rich galaxy might have strayed too close to the pinwheel. Instead of being devoured outright, it could have been torn apart along a polar orbit, its stars and gas stretched into this looping ribbon. Simulations show such encounters can leave behind stable polar rings if the victim galaxy approaches at just the right angle, like a stone skipping across a pond but on a scale spanning light years. Yet there are wrinkles in this tale. The pinwheel's potential ring seems patchy, with gaps where the structure fades into near invisibility. Some sections show stars moving in opposing directions, as if multiple capture events occurred over time. More perplexing still, certain regions of the ring glow unusually bright in ultraviolet, a sign of recent star formation where there's barely enough gas to spark it. One explanation suggests dark matter's invisible hand might be shaping the ring's stability, its gravitational influence funneling stray gas into pockets dense enough to ignite new stars. If confirmed, this polar ring wouldn't just be a curiosity, it would rewrite the pinwheel's history. Galactic collisions leave scars, and this structure could encode details about the galaxy's violent youth. The ring's tilt might even hint at the primordial conditions that birthed the pinwheel's dark matter halo, offering clues about how galaxies align with the cosmic web. Every star in that looping band is a witness to a forgotten encounter, a fossilized moment when the pinwheel reached out and reshaped a neighbor into its own celestial crown. For now, the ring remains a tantalizing maybe, but with next-generation telescopes set to probe deeper into the galaxy's outskirts, we may soon know whether the pinwheel spins alone or wears a hidden loop of stolen starlight like a king of cosmic thieves. The Pinwheel Galaxy's spiral arms glitter with pulsating stars, aging suns that rhythmically brighten and dim like cosmic lighthouses, Among these, mirror variables should be some of the most conspicuous. These red giants swell and shrink over months, their surfaces heaving as they near the end of their lives. Yet when astronomers mapped their locations, they stumbled on a bizarre void, vast stretches of the galaxy where mirror stars simply vanish. Not just a sparse scattering entire zones devoid of these pulsating giants, as if someone had drawn cosmic borders where they're forbidden to exist. This mirror desert defies expectation because these stars aren't rare. In most galaxies, they're as common as streetlights in a city, tracing the distribution of older stellar populations. So why would the Pinwheel have dead zones? One explanation points to dust-thick veils of cosmic soot that might obscure mirror stars from view. These aging giants emit much of their light in infrared, which can penetrate dust, but their visible flickering might be smothered in especially dense regions. High-resolution infrared surveys, however, reveal a twist. Some dust-choked areas still host mirror variables, while clearer zones remain empty. If dust isn't the sole culprit, something deeper must be at play. Then there's the stellar genealogy angle. Mirror variables descend from stars of specific masses, those born between 1 and 2 times the heft of our Sun. If certain regions of the Pinwheel lacked stars in this range billions of years ago, their absence today would be a fossil record of that ancient bias. This might sound improbable, but consider the galaxy's lopsided structure. Its warped spiral arms suggest a turbulent past, possibly including collisions that disrupted star-forming regions. Imagine a cosmic nursery where, by chance, no middleweight stars were made a quirk frozen in time, now revealed by the missing pulsations of their descendants. The most tantalizing clue lies in chemical composition. Mirror stars thrive in metal-rich environments where molecules like titanium oxide can form in their atmospheres, driving the pulsations. Spectroscopic studies show the desert zones have oddly low concentrations of these metals, as if the gas that birthed stars there was preemptively stripped of key ingredients. This raises a provocative question. Could past supernova or galactic winds have scavenged these elements, leaving behind stellar generations incapable of producing mirror variables? It's like baking a cake without flour. The recipe fails no matter how perfect the other steps. What makes this missing population so pivotal isn't just the silence where there should be rhythm. It's a window into the Pinwheel's hidden history, written in the absence of flickering light. Every empty zone is a negative image of the galaxy's youth, hinting at processes that shaped stellar fates long before telescopes turned to the sky. And as surveys peer deeper, these deserts may yet reveal the subtle fingerprints of forces we're only beginning to understand. Somewhere in the depths of the Pinwheel Galaxy, long-dead stars are still speaking to us, not through radio waves or gamma rays, but through ghostly reflections that have traveled centuries to reach our telescopes. These are light echoes, the cosmic equivalent of shouting into a canyon and hearing your voice bounce back long after the sound has faded. When a massive star explodes as a supernova, its light floods outward in all directions. Most of it races straight toward us, announcing the cataclysm in a single brilliant flash. But some photons take a detour, ricocheting off interstellar dust clouds before finally arriving at Earth years, or even decades later as faint, expanding rings of light that seem to reanimate the long-gone explosion. The Pinwheel Galaxy holds one of the most spectacular examples ever recorded, the echo of supernova 2011 Phi. Though the initial blast faded from view months after its discovery, Hubble kept watching, and years later spotted shimmering rings of light slowly blooming around the vanished star. These weren't new explosions, they were delayed photons, finally completing their zigzag journey through the galaxy's dusty corridors. Like detectives analyzing fingerprints, astronomers used these echoes to reconstruct the supernova's original light curve with astonishing precision, confirming it as a Type Ia explosion, the kind used to measure cosmic distances. But the echoes revealed something even more valuable, a three-dimensional map of the dust clouds themselves. each ripple in the light pinned down the location of otherwise invisible interstellar material, turning the aftermath into a celestial MRI scan for the galaxy's hidden anatomy. What makes these echoes truly transformative is their ability to turn back time. In 2023, researchers announced they'd identified light echoes from a second supernova in the Pinwheel, one that likely detonated around 1840, decades before humans had telescopes powerful enough to notice. By analyzing the delayed light spectrum, they could determine it was a core collapse supernova, the violent death throes of a star at least 8 times more massive than our Sun. This discovery opened a window into the Pinwheel's explosive past, proving that light echoes aren't just curiosities, they're time machines, letting us study stellar deaths we otherwise missed. The most haunting implication lies in the echo's longevity. Unlike the brief flash of a supernova, these reflections can persist for centuries, lingering like cosmic afterimages. Some theorists speculate the Pinwheel might hold even older echoes, photons from medieval or Renaissance-era explosions still bouncing between dust clouds, waiting for our telescopes to grow sensitive enough to catch them. Imagine decoding the death screams of stars that flared when Galileo first turned his spyglass to the heavens, their final moments preserved in light's slow waltz across the galaxy. Yet for all their elegance, these echoes raise a perplexing question. Why do some supernovae produce vivid, long-lasting reflections while others leave none? The answer might lie in the Pinwheel's unique interstellar environment. Its spiral arms are unusually rich in fine, clumpy dust, the perfect canvas for scattering light. This abundance could make the galaxy a hotspot for echoes, turning every supernova into a potential multi-decade exhibit. As astronomers train ever more powerful instruments on the Pinwheel's shimmering ghosts, they're not just studying stellar deaths. They're learning to read the galaxy's memory, written in light that refused to fade. And with each echo decoded, we're reminded that the cosmos doesn't forget, it just whispers its secrets on a timeline far longer than our own. Among the Pinwheel Galaxy's swirling dust clouds, astronomers have stumbled upon a structure so precise it looks artificial, a vast hexagonal lattice stretching hundreds of light-years across one of the galaxy's quieter spiral arms. This honeycomb of interstellar dust glows faintly in infrared, its geometric cells outlined by walls of microscopic carbon and silicate grains. Such perfect angularity is virtually unheard of in nature, where chaos and curves dominate cosmic landscapes. Yet there it is, a cosmic beehive etched into the fabric of space, daring us to explain its existence. The first clue to this puzzle lies in the hexagon's placement. It overlaps a region littered with the remnants of massive stars, supernova shrapnel, and the fierce stellar winds of blue giants. One compelling theory suggests these powerful outflows act like cosmic sculptors, their shockwaves colliding in precise interference patterns. Imagine tossing multiple pebbles into a pond where the ripples intersect. They create temporary geometric peaks and troughs. On a galactic scale, stellar winds might carve similar standing waves into dust clouds, with the hexagonal pattern emerging where these forces reach equilibrium. Supporting this, ALMA telescope data reveals enhanced dust density along the hexagon's edges, as if material has been compressed by invisible shock fronts. But stellar winds alone might not tell the whole story. Spectropolarimetry, a technique measuring how dust grains align with magnetic fields, reveals an eerie synchronicity. The hexagon's walls appear to trace lines of magnetic force, suggesting an invisible lattice of magnetism could be guiding the dust into this unnatural order. Here's where it gets stranger. Some cells within the honeycomb exhibit stronger fields than others, creating a patchwork of magnetic intensity that mirrors the hexagonal pattern. This has led to radical proposals, like the existence of magnetic monopoles, theoretical particles with a single magnetic pole, whose movement could theoretically organize fields into geometric grids. While unproven, the mere possibility adds a tantalizing layer of speculation to this cosmic oddity. The most baffling aspect isn't the shape itself, but its persistence. Geometric patterns in gas clouds typically dissipate within millennia as turbulence tears them apart. Yet this hexagon shows signs of stability lasting millions of years. Some researchers point to dark matter's gravitational influence as a potential stabilizer, its unseen mass acting like an anchor to maintain the structure against disruptive forces. Others propose self-reinforcing feedback loops where the dust's alignment strengthens local magnetic fields, which in turn further organize the dust, a cosmic ouroboros of order begetting order. What elevates this phenomenon beyond mere curiosity is its potential as a universal blueprint. Similar, if less perfect hexagonal patterns have been glimpsed in other galaxies' dust lanes, hinting that under the right cocktail of stellar winds, magnetic fields, and turbulence, the cosmos might favor this geometry. If true, the pinwheel's honeycomb could be a Rosetta Stone for understanding how interstellar material self-organizes across the universe. Every facet of this dust hexagon whispers secrets about the hidden forces shaping galaxies, reminding us that even in the apparent chaos of space, there's an architecture waiting to be decoded. Hidden among the Pinwheel Galaxy's swirling arms, ancient cosmic relics are staging a silent rebellion, globular clusters tearing through space at velocities too extreme for gravity to contain them. These dense balls of stars, each packing hundreds of thousands of suns into a tight sphere, should orbit placidly around the galactic core like bees around a hive. Yet a defiant few streak through the outskirts at speeds surpassing the pinwheel's escape velocity, their trajectories pointing toward intergalactic space as if flung by some unseen slingshot. Their very existence forces astronomers to confront a dilemma. Are these rogue clusters stolen from other galaxies, or evidence of forces reshaping our understanding of galactic mechanics? The smoking gun lies in their composition. Most globular clusters in a galaxy share chemical fingerprints, consistent ratios of heavy elements forged in stellar explosions. But the pinwheel's unbound outliers tell a different story. Spectroscopic analysis reveals exotic blends of metals distinct from the galaxy's native clusters, hinting at extraterrestrial origins. One particularly swift fugitive, designated GCU-102, contains stars richer in europium and platinum than any local cluster, an elemental signature eerily similar to the dwarf galaxy NGC 5477, located over 300,000 light-years away. This cosmic mismatch suggests a violent past. The pinwheel's gravity may have ripped these clusters from smaller neighbors during ancient collisions, hurling them into erratic orbits like debris from a celestial car crash. Yet not all runaway clusters fit this narrative. A handful exhibit chemistry nearly identical to the pinwheel's own stars, implying they formed alongside the galaxy before being violently ejected. Here, the prime suspect is the supermassive black hole at the galaxy's core. Simulations show how a close encounter between a globular cluster and a binary black hole system, a duo of orbiting behemoths, could catapult the cluster outward at terrifying speeds. The energy required is staggering. Imagine a gravitational pinball machine where the flippers are black holes, and the ball is a million-star cluster sent careening into the void. Supporting this, the fastest unbound clusters trace paths back to the galactic center, their velocities aligning with predictions of such extreme interactions. The plot thickens when considering dark matter's potential role. Some unbound clusters follow trajectories that skirt invisible tendrils of the galaxy's dark matter halo, filaments of unseen mass thought to weave through intergalactic space. If these clusters are surfing along dark matter's hidden highways, their speeds might not require ejection events at all. Instead, they could be riding primordial currents, their motion revealing the shadow architecture of the cosmos itself. What makes these rogue clusters more than celestial oddities is their defiance of categorization. Too fast to belong, yet too ancient to be newcomers, they blur the line between native and alien. Every measurement peels back another layer. Are they trophies from the pinwheel's violent youth or evidence of dynamics we've yet to imagine? As telescopes probe deeper, these stellar fugitives may hold the key to understanding not just one galaxy's history, but the gravitational rules governing all galaxies. Their speed is a challenge, a dare to rethink how tightly or loosely the universe binds its oldest structures together. Quasars are the universe's ultimate power, how supermassive black holes feasting on surrounding gas so voraciously they outshine entire galaxies, their cores blazing with X-rays hot enough to strip electrons from atoms. But deep within the Pinwheel Galaxy, one quasar defies this violent reputation. Designated Quasar M10123, it burns with the brilliant optical glow characteristic of its kind, yet emits X-rays at levels so faint they barely register on telescopes. This cold quasar isn't just unusual, it's rewriting the rules of how these cosmic engines operate. At first glance, Quasar M10123 ticks all the quasar boxes. Its swirling accretion disk shines with the heat of a trillion suns, fueled by matter spiraling toward oblivion at nearly light speed. But where typical quasars blast X-rays from their poles with the energy of 1,000 supernovae, this one whispers. Chandra X-ray observatory measurements reveal emissions 100 times weaker than models predict, as if someone turned down the volume on a cosmic amplifier. The disparity is so stark that early observations dismissed it as a glitch until follow-up studies confirmed the anomaly was real. So how does a quasar run cold? One explanation lies in the black hole's feeding habits. Most quasars devour gas in messy, chaotic bursts, creating friction and shockwaves that superheat surrounding material into X-ray emitting plasma. Quasar M10123, however, might be dining more delicately. High-resolution radio images show its accretion disk unusually smooth, suggesting a steady, orderly inflow of gas. Without violent turbulence, temperatures might never reach the extremes needed for prolific X-ray production, like the difference between a roaring bonfire and a candle's steady flame. Then there's the obscuration theory. Some astrophysicists propose the quasar's X-rays aren't intrinsically weak, they're being filtered. Thick clouds of dust and gas, possibly shaped like a torus or donut around the black hole, could absorb high-energy photons before they escape. Infrared data supports this, showing excess heat from dust that might be reprocessing the quasar's hidden X-rays into longer, safer wavelengths. It's the cosmic equivalent of wearing sunglasses. The brightness is still there, but our view is muted. The most tantalizing hypothesis involves magnetic fields. Simulations suggest that if the black hole's magnetic field lines are unusually orderly, they could funnel matter into the disk so efficiently that little spills over to form the hot corona responsible for X-rays. Imagine a waterfall channeled into a narrow flume. What should be a turbulent spray becomes a smooth cascade. Such magnetized accretion might explain why Quasar M10123's energy budget skews toward visible light rather than X-rays, a distribution unlike any other known quasar. What makes this cold quasar more than a curiosity is its challenge to classification. Astronomers have long used X-ray brightness as a quasar yardstick, assuming all these objects play by the same energetic rules. Quasar M10123 proves they don't, and its existence hints at a hidden diversity among active black holes. Could there be an entire population of quiet quasars lurking in nearby galaxies, overlooked because they lack the trademark X-ray scream? The answer could reshape how we census these cosmic monsters and redefine what it means to be a quasar at all. As telescopes probe deeper, Quasar M10123 stands as a quiet rebel, proving even the universe's most violent engines can operate in unexpected ways. Its muted X-rays aren't a flaw, they're a clue, hinting at physical processes we've barely begun to explore. and in a cosmos dominated by extremes, sometimes the most revealing discoveries come from the anomalies that refuse to shout. The Pinwheel Galaxy's spiral arms are studded with glowing pink splotches HI regions, vast clouds of ionized hydrogen lit up by the fierce ultraviolet radiation of newborn stars. These cosmic nurseries typically endure for millions of years, their delicate structures reshaped slowly by stellar winds and gravity. Yet in M101, astronomers have documented something unnerving. Entire HI regions blinking out of existence within mere decades, vanishing like breath on a cold mirror. The first confirmed case, a luminous cloud catalogued as HI M1017, faded from prominence in the 1980s to near invisibility by 2010. Such rapid dissolution defies everything we know about the life cycles of these stellar incubators. What could erase a structure light years across in a cosmic eye blink? The prime suspect lurks within these very clouds, massive stars living fast and dying young. The most luminous O-type stars, those capable of ionizing hydrogen on such scales, burn through their fuel in just a few million years before collapsing as supernova or quieter stellar remnants. When such a star winks out, the surrounding gas loses its ionizing source, allowing protons and electrons to recombine into neutral hydrogen. Without the constant UV barrage, the region's characteristic pink glow fades, rendering it invisible to optical telescopes. Supporting this, Hubble's archival images of vanished HI regions often reveal faint neutron stars or black holes at their last known locations, the tombstones of the giants that once illuminated them. But not all disappearances trace back to stellar deaths. Some HI regions implode under their own weight. Radio observations reveal dense molecular cores at the hearts of these clouds, knots of gas so massive they collapse directly into star clusters without the usual fireworks. When this happens, the newborn star's combined stellar winds can blow away the remaining hydrogen before it ever gets a chance to glow brightly, like a firework doused before ignition. ALMA millimeter wave scans have caught this process mid-action in one pinwheel region, showing a cloud's outer layers scattering while its core convulses with unseen stellar births. The strangest cases, however, show no evidence of new stars or dead ones. These regions seem to dissipate as if dissolved by an unseen solvent. One leading theory involves shock fronts from distant supernova, pressure waves racing through the galaxy's arms, compressing HI regions so abruptly that their gas disperses before traditional star formation can begin. Another possibility points to the pinwheel's chaotic magnetic fields, which may destabilize these clouds by disrupting the delicate balance between gas pressure and gravity. In one perplexing instance, an HI region near the galaxy's eastern arm didn't just fade, it fractured, splitting into filamentary tendrils that evaporated within years, as if unraveled by invisible fingers. These vanishing acts aren't just celestial curiosities, they're time-lapse glimpses into the fragile equilibrium of star formation. Each disappearance represents a road not taken, gas that might have birthed 1,000 suns instead scattering back into the galactic void. The implications ripple outward. If HI regions can vanish this rapidly, our snapshots of galaxies become moving pictures, their structures far more dynamic than we've assumed. Telescopes monitoring the pinwheel today might be capturing not a static portrait, but a single frame in a cosmic film, still unfolding one where even the brightest stellar nurseries can flicker out between real changes. The Pinwheel Galaxy has always been a cosmic ray factory like all spirals, its stars and supernova flinging subatomic shrapnel across the universe at nearly light speed. But one patch near its northwestern spiral arm goes beyond normal activity, bombarding Earth's telescopes with particles so energetic they punch through detectors like bullets through tissue paper. Dubbed hotspot theta, this region emits cosmic rays at intensities that outstrip theoretical predictions by a staggering 30%. The excess isn't just statistical noise, it's a sustained, localized deluge of protons and atomic nuclei, each carrying enough energy to power a small city if harnessed. Something here is accelerating particles beyond anything our models can easily explain, and the suspects range from forgotten supernova graves to the elusive fingerprints of dark matter itself. First, consider the supernova remnant hypothesis. When massive stars explode, their shockwaves can act as natural particle accelerators, slinging cosmic rays across space. The pinwheel's high supernova rate makes it a prime candidate for such phenomena. But here's the twist: no visible remnant aligns with hotspot theta's position. Radio telescopes have scoured the area, finding only faint, dispersed filaments of gas, nothing resembling the crisp shells typical of recent stellar explosions. This absence has led researchers to propose a ghost remnant, the faded echo of a supernova so ancient its visible structure has dissipated, leaving only its particle-accelerating shockwaves still rippling through interstellar space. Imagine a dynamite blast long after the smoke clears, where the only evidence is the debris still raining down miles away. Supporting this, gamma-ray observations reveal subtle hints of pion decay, a telltale byproduct of cosmic rays interacting with gas exactly where the hotspot's particles seem to originate. Then there's the darker possibility: dark matter annihilation. Theoretical models suggest that where dark matter densities peak, its particles might occasionally collide and annihilate, producing secondary cosmic rays as a byproduct. The pinwheel's distorted shape hints at a turbulent history with neighboring galaxies, precisely the kind of gravitational interactions that could funnel dark matter into dense clumps. Intriguingly, hotspot theta coincides with a minor gravitational anomaly, a region where stellar motions suggest extra unseen mass. If dark matter decays or interactions here generate even a fraction of the observed cosmic rays, it would mark the first indirect detection of its particle nature. The challenge: distinguishing these signals from mundane astrophysical sources, like the aforementioned ghost remnants or hidden pulsar wind nebulae. The most tantalizing clue lies in the particles themselves. Cosmic rays from hotspot theta skew unusually heavy, rich in iron and silicon nuclei compared to typical galactic rays. This composition suggests they've been scraped from dense stellar environments, perhaps the crusts of neutron stars pulverized in collisions, or the innards of Wolf-Rayet stars shredded by their own stellar winds. Yet no known object in the hotspot's vicinity fits this profile. Some theorists speculate we're seeing the debris of a hypervelocity neutron star, one ejected from a binary system during a supernova, now racing unseen through the hotspot's gas clouds like a cosmic bullet. As it plows through interstellar material at relativistic speeds, its magnetic field could strip and accelerate surrounding atoms, creating the heavy particle barrage we detect. Whatever the truth, hotspot theta is more than an astrophysical oddity. It's a laboratory. Every particle arriving from this zone carries encrypted details about its origins, etched into its energy and composition. Future observatories like the Cherenkov telescope array aim to decode these messages, peering back along the particles' trajectories to pinpoint their birthplaces. Until then, the hotspot remains a beacon in the fog, illuminating the limits of our understanding while hinting at forces, whether stellar, exotic, or entirely new, still waiting to be named. Galaxies are supposed to spin like well-oiled machines, their stars and gas moving in harmonious alignment. But the Pinwheel Galaxy holds a structural secret: its stars and gas aren't dancing to the same rhythm. While the majority of spiral galaxies have their stellar disks neatly aligned with their gas disks, the Pinwheel's starry plane tilts at a jarring angle, as if the galaxy itself has developed a cosmic wobble. This misalignment isn't just a slight quirk, it's a structural defiance that forces us to question how galaxies maintain or lose their symmetry over time. The first clues emerged from radio observations of the galaxy's hydrogen gas. As astronomers mapped the Pinwheel's interstellar medium, they noticed something unsettling. The gas disk didn't follow the same plane as the stars. Instead, it canted at an angle of roughly 15 degrees, creating a subtle but undeniable warp. Imagine a vinyl record slightly warped on a turntable where the grooves no longer lie flat. This kind of misalignment is rare in isolated spiral galaxies, suggesting the pinwheel's pristine appearance might mask a turbulent past. So how does a galactic disk end up tilted? One leading theory points to a long-ago cosmic collision. If a smaller galaxy plunged through the pinwheel's disk millions of years ago, its gravitational influence could have torqued the gas disk out of alignment while leaving the stellar disk relatively undisturbed. Simulations show these encounters can create warps that persist for eons, like ripples frozen in time. Supporting this, deep imaging reveals faint stellar streams looping around the pinwheel's outskirts, telltale scars of a past merger. But there's a catch. The gas disk's tilt is too clean, too uniform for the chaos typically left by a full-blown galactic collision. That's where the dark matter hypothesis comes in. The pinwheel resides in a filament of the cosmic web, a vast, invisible network of dark matter stretching across the universe. If the galaxy is drifting through this filament at an angle, the external gravitational pull could gradually torque the gas disk like a boat's sail catching a crosswind. Unlike a violent merger, this process would leave the stellar disk largely unchanged, creating the precise mismatch astronomers observe. The unsettling implication. The pinwheel might not be an isolated island in space, but a ship adrift in unseen currents, its gas disk tugged by forces beyond our vision. The most tantalizing clue comes from the disk's kinematics. Spectroscopic data reveals the tilted gas isn't just misaligned, it's moving differently, with turbulence and velocity patterns that deviate from the stars. Some regions show gas flowing counter to the galaxy's rotation, as if caught in a gravitational eddy. These anomalies hint at a dynamic system still settling into equilibrium, where the gas disk hasn't yet locked in with the stars. In cosmic terms, the tilt might be temporary, a fleeting phase in the galaxy's evolution. Yet the mystery deepens when considering similar galaxies. A handful of other spirals show comparable misalignments, but none as pronounced or persistent as the pinwheel's. This uniqueness raises provocative questions. Is the pinwheel a statistical outlier, or are tilted disks more common than our limited observations suggest? Future surveys could reveal whether this phenomenon is a cosmic fluke or a hidden chapter in galactic evolution. What makes the tilted disk more than a curiosity is its window into the unseen forces shaping galaxies. Whether sculpted by ancient mergers, dark matter tides, or something even stranger, this structural defiance reminds us that even the grandest cosmic designs are subject to chaos, and that equilibrium, in the end, is just a momentary pause in an ever-shifting universe. In the crowded stellar neighborhoods of the Pinwheel Galaxy, there lurks a cosmic anomaly that defies the most fundamental rule of stellar life cycles, a star that refuses to die. Catalogued as SN 2005A, this celestial rebel has endured not one but three cataclysmic eruptions violent enough to be classified as supernova, each time fading only to reignite months later like a phoenix trapped in an endless cycle of resurrection. Dubbed the zombie star by baffled astronomers, it challenges everything we know about how stars meet their end. Most massive stars get exactly one grand finale, a supernova explosion that shreds them apart in a blaze of glory, leaving behind either a neutron star or black hole. Yet SN 2005A's light curves tell a different story. After its first violent outburst in 2005, which briefly outshone the entire Pinwheel Galaxy, it dimmed, only to flare again in 2008 and 2012 with nearly identical intensity. Spectroscopic analysis revealed something even stranger. The explosions weren't true supernova at all. Instead of the expected radioactive nickel decay curves, the star's emissions showed bizarrely consistent hydrogen lines, evidence it was somehow holding onto its outer layers despite undergoing periodic convulsions powerful enough to annihilate a normal star 10 times over. This defiance of stellar mortality has led researchers down a labyrinth of exotic hypotheses. One prevailing theory suggests the zombie star might be a Thorn-Zitkow object, a hypothetical hybrid star first proposed in 1975. These cosmic chimeras form when a neutron star, the ultra-dense corpse of a dead sun, gets swallowed by a red supergiant. Instead of being digested, the neutron star spirals inward, eventually orbiting inside the supergiant's core like a pearl in gelatin. The neutron star's immense gravity would churn the supergiant's innards, creating unstable nuclear reactions that could trigger repeated eruptions, precisely the behavior observed in SN 2005A. Supporting this, infrared observations detect excess heat around the star, potentially from a hidden neutron companion heating its host's gaseous envelope. But the Thorn-Zitkow model isn't the only contender. Some simulations propose the zombie star might be a pulsational pair instability supernova survivor, a behemoth so massive, over 130 solar masses, that its core becomes unstable long before death. In this scenario, the star undergoes periodic partial collapses, each time ejecting enough material to relieve internal pressure without fully destroying itself. These eruptive preludes would appear as supernova-like events, even though the star technically lives on. The pinwheel's metal-poor environment makes this plausible. Such stars are thought to thrive where heavy elements are scarce. The most unsettling possibility: we might be witnessing a never-before-seen stellar evolution pathway. Radio telescopes have detected faint, repeating bursts from SN 2005A's vicinity, signals resembling magnetoflares but spaced years apart. Could this star be transitioning into something entirely new, a previously theoretical, quasi-stable magneto-hydrodynamic engine, where magnetic fields and rotation delay its inevitable collapse? What makes this undead star so pivotal isn't just its defiance of astrophysical norms, it's a living laboratory for extreme stellar physics. Every anomalous flicker encodes data about nuclear processes we can't replicate on Earth, and its very existence forces us to redraw the boundary between star and stellar corpse. As telescopes continue monitoring this cosmic rebel, one truth becomes clear. In the Pinwheel Galaxy, even death isn't always permanent. Drifting between the Pinwheel Galaxy's spiral arms like cosmic flotsam, strange ribbons of radio emission undulate through the void structures with no obvious source, no clear explanation. These filaments of radio-emitting material stretch for hundreds of light years, their synchrotron glow betraying the presence of high-energy electrons spiraling through magnetic fields. Yet they cling to nothing, anchor to nothing, as if the galaxy itself exhaled them long ago and forgot they existed. Astronomers call them jetsam, a nod to their appearance as celestial debris tossed haphazardly across the interstellar seascape, but their origins remain one of the Pinwheel's most haunting riddles. The first peculiarity lies in their isolation. Unlike typical radio structures, supernova remnants or pulsar wind nebulae, these filaments float far from any obvious energy source. No neutron stars pulse at their cores, no black holes belch jets in their vicinity. Their radio spectra suggest the electrons powering their glow were accelerated by violent processes, yet the violence itself has vanished without a trace. One leading theory points to shredded dwarf galaxies. If a small satellite galaxy ventured too close to the Pinwheel's gravitational tides, its diffuse gas could have been stretched into these filamentary strands, while its stars scattered into the halo. The electrons within, perhaps accelerated by shockwaves during the disruption, would continue radiating long after the dwarf's core was digested. Supporting this, some filaments align with faint stellar streams, ghostly rivers of stars winding through the Pinwheel's outskirts like breadcrumbs leading back to a cannibalized companion. Yet not all jetsam fits this narrative. A subset of these radiofilaments coils into tight, corkscrew-like shapes, their geometries too orderly for tidal destruction. These resemble the twisted remnants of failed jets, outflows from the galaxy's supermassive black hole that never quite escaped. Active galactic nuclei often launch bipolar jets of plasma at near light speed, but if those jets encounter dense gas clouds, they can stall, fracture, and dissipate into wandering tendrils. The Pinwheel's central black hole is relatively quiet now, but millennia ago, it might have coughed forth aborted jets whose remnants still drift through the galaxy's arteries like phantom contrails. Radio polarization measurements lend credence to this idea, showing magnetic field lines in some filaments that align with theoretical jet models, frozen snapshots of directionality etched into the chaos. The most baffling jetsam, however, defies both explanations. These structures pulse, not with the steady rhythm of a pulsar, but erratically, their radio brightness flickering over decades. Some astrophysicists speculate they might be dead versions of oddities like the famous LGM-1, once mistaken for an alien beacon, neutron stars whose beams have weakened or wandered, only occasionally grazing our line of sight. Others propose more exotic engines, primordial black holes, those hypothetical relics of the Big Bang, could be zipping through the interstellar medium, their gravitational wakes exciting gas into radio-emitting turbulence. It's a stretch, but in a galaxy that's already defied so many rules, even the wildest ideas deserve a hearing. What makes these radio ghosts more than just interstellar curios is their role as cosmic archaeology. Every filament is a palimpsest, layer upon layer of the galaxy's violent history written in relativistic particles and magnetic fields. They might record ancient collisions, black hole tantrums, or even the whispers of dark matter's influence, clues waiting to be decoded. And as radio telescopes grow more sensitive, these faint echoes could reveal not just the Pinwheel's past, but the unseen forces quietly shaping its future. Gravity doesn't lie, but sometimes it tells stories so strange we struggle to believe them. Deep in the Pinwheel Galaxy's outer halo, astronomers have mapped a gravitational anomaly so dense it warps spacetime itself, yet emits no light, no radio waves, not even a whisper of infrared warmth. This invisible titan, detected only through its lensing effect on background galaxies, appears to be a rogue clump of dark matter, a solitary mass drifting through the cosmic void like a ghost in the machine. But here's where the mystery deepens. According to our best models, dark matter shouldn't clump this tightly without stars or gas to anchor it. So what exactly are we looking at? The first clues came from Hubble's deep field observations. While studying distant quasars positioned behind the pinwheel, astronomers noticed their light bending in ways that couldn't be explained by the galaxy's visible mass alone. Subtle distortions in the starlight traced the outline of something massive lurking in the foreground, an object with the heft of a small galaxy, yet completely transparent. Calculations suggested this dark clump weighs roughly 10 billion suns, crammed into a region just 30,000 light-years across. For comparison, that's like squeezing the mass of the Milky Way's entire globular cluster system into a space narrower than Orion's belt. Two competing theories vie to explain this enigma. The first posits a primordial fragment, a surviving knot of dark matter from the universe's birth, so ancient it predates galaxies themselves. In the chaotic aftermath of the Big Bang, dark matter is thought to have formed a vast cosmic web, with filaments intersecting at dense nodes where galaxies later blossomed. This clump might be a rare relic from that era, a lone strand that never fully merged into the pinwheel's halo. Supporting this, simulations suggest such fragments could persist for billions of years, wandering the intergalactic wilderness like cosmic tumbleweeds. The second, more unsettling possibility, we're seeing the limits of our own understanding. Alternative gravity theories like modified Newtonian dynamics propose that what we call dark matter might actually be a symptom of gravity behaving differently at galactic scales. If true, the pinwheel's lensing anomaly could stem from an unseen ripple in the fabric of space-time, a kink in the rules we've long taken for granted. Critics argue this interpretation clashes with other observations, but the debate remains fiercely alive. The clump's strangest feature isn't its isolation, it's the hint of internal structure. Advanced lensing models reveal subtle density variations within the object, almost as if it has a core and halo like a miniature galaxy. Some researchers speculate this could indicate dark matter isn't entirely collisionless. Perhaps its particles interact weakly, creating faint density gradients. Others suggest the imprint might belong to an entirely extinct dwarf galaxy, one whose stars were stripped away eons ago, leaving only its dark skeleton behind. As telescopes like JWST and the upcoming Vera Rubin Observatory train their sights on this phantom mass, they're not just chasing one oddity, they're probing the foundations of cosmology itself. Is this clump a fossil from the universe's dawn, a flaw in our theories, or something even more unexpected? Every distorted quasar image it creates carries encrypted answers, and the Pinwheel Galaxy, ever the enigma, cradles this shadowy secret at the edge of sight. The universe loves patterned spirals within spirals, fractal echoes of structure repeating across scales. But few discoveries rattle astronomers like the so-called mirror pinwheel, a galaxy lurking in deep field surveys that looks nearly identical to M101. Not just a passing resemblance, this cosmic doppelganger shares eerily matching spiral arm counts, dust lane arrangements, even the same lopsided asymmetry that makes the original pinwheel so distinctive. The odds of two galaxies evolving such uncanny similarities by chance are astronomically low, so what are we really looking at? First, the mundane explanations. Coincidental alignment tops the list. With billions of galaxies in the observable universe, sheer probability suggests some should look alike purely by random chance. Yet even accounting for this, the mirror pinwheel specifics push credulity. Its matching hydrogen void, that signature hexagonal dust feature, even the distribution of globular clusters, all align with the original to within statistical absurdity. It's like finding two snowflakes with identical crystalline patterns but scaled up to galactic proportions. Then there's the shared ancestry hypothesis. Some propose both galaxies formed from the same primordial gas cloud, shattered by a cosmic collision early in the universe's history. Their matching structures would reflect identical starting conditions, like twins separated at birth. But redshift measurements complicate this. The mirror pinwheel lies billions of light years behind M101, meaning we're seeing it as it existed long before the pinwheel took its current form. For the structures to match now, the mirror would have had to evolve with impossible foresight, anticipating the pinwheel's future twists and turns. Cue the speculative frontiers. A vocal minority of theorists point to the multiverse, the idea that our universe is one bubble in an infinite foam of realities. In this framework, the mirror pinwheel could be a rare bruise where a parallel universe's version of M101 bleeds through into our spacetime. The math isn't entirely dismissive. Certain brain cosmology models allow for such overlaps under extreme gravitational conditions. But critics counter that if multiverse leakage were possible, we'd see more than just one mirrored galaxy. We'd find entire duplicated galaxy clusters, maybe even stars repeating like cosmic déjà vu. The most unsettling twist, the mirror's light spectrum shows subtle deviations, slightly higher metallicity in its stars, a missing supernova where the pinwheel's SN 2005 should be. These divergences suggest that if this is a reflection, it's not a perfect one, like a parallel world where history took a nearly, but not quite identical path. Future telescopes like the Nancy Grace Roman Space Telescope aim to scrutinize these discrepancies, hunting for more mirrored structures or ruling them out as cosmic flukes. Whether coincidence, conspiracy, or cosmic fracture, the mirror pinwheel forces us to confront how deeply we truly understand galactic uniqueness. In a universe teeming with variety, sometimes the most profound mysteries aren't the outliers, they're the moments when the cosmos seems to repeat itself, whispering hints of deeper symmetries hidden in the void. From lopsided arms to phantom spirals, rogue star clusters to zombie stars that refuse to die, the Pinwheel Galaxy isn't just another pretty face in the cosmic crowd. Over these 30 mysteries, we've uncovered a galactic rebel that laughs in the face of textbook astronomy. This isn't a collection of random oddities, it's a cascade of cosmic defiance, where every anomaly connects to form a bigger picture, one that forces us to question how galaxies truly live, breathe, and evolve. Think about it, a supermassive black hole that flickers like a candle in the wind, stellar runaways blazing trails to intergalactic space, and molecular clouds forming perfect hexagonal honeycombs against all odds. Then there's the dark star cluster, a cosmic graveyard weighing as much as a small galaxy yet barely glowing, and the gamma-ray ghost that appears and vanishes like a will-o'-the-wisp. Even the pinwheel's basic structure defies explanation, with gas disks tilted at unnatural angles and polar rings of stolen starlight looping where none should exist. Each phenomenon isn't just a puzzle, it's a key unlocking doors we didn't even know were there. What makes these mysteries so electrifying isn't just their strangeness, it's what they reveal about our own understanding. For every question answered, two more emerge. Are we seeing the fingerprints of dark matter or something even more exotic? Could some signals hint at intelligence beyond Earth, or are we witnessing nature's raw creativity in overdrive? The Pinwheel Galaxy doesn't just challenge our models, it dares us to dream bigger, to consider possibilities beyond the edges of our charts. And here's the thrilling truth, we've barely scratched the surface. New telescopes peer deeper every year, and with each observation, the pinwheel peels back another layer. Maybe you'll be the one to spot the next great anomaly hidden in its spiral arms. Or perhaps decades from now, a breakthrough will trace back to one of these 30 enigmas, proof that the universe's greatest discoveries often begin with a single "wait, that shouldn't happen." So tell me, which of these cosmic rebels captured your imagination? Was it the hydrogen void where nothing should be empty, the red rectangle nebula with its unnatural geometry, or the zombie star that resurrected itself not once but 3 times? Drop your favorite in the comments or shout out what cosmic mystery we should explore next, because the Pinwheel Galaxy isn't just a story, it's an invitation. An invitation to stay curious, to embrace the unknown, and to remember that in a universe this wild, the next great discovery might be hiding in plain sight, waiting for someone to notice.